Hi everybody, Patrick here from EscapeRoomElectronics.com, EngineeringShock.com, and PaintballProps.com. This is Project 10 for the Arduino Playbot. The Kickstarter campaign is linked below. This project will include our external resistor-based keypad, the Playbot itself, and the 3-pin connector cable. And in this video what we're going to do is we are just going to experiment with analog to digital conversion based on the resistor keypad, and we're going to read it out on the LCD. So to understand this project, what we've got here is a resistor keypad that outputs a certain voltage depending on which button you're pressing. The analog input to the Arduino Playbot takes that analog input, changes it into a digital representation between 0 and 1024, and displays it on the LCD. And using these values and the explanation coming up of how the resistor-based keypad works, we're going to be able to decode, using software, which button is being pressed. We'll turn those digital representations into 1, 2, 3, 4, 5, 6, 7, 8, 9, or 10. And we'll be doing that in the next video. And in the last video, we'll be doing a full combination lock with EEPROM memory. So, first things first, let's hook it up and then we'll talk about the resistor-based keypad schematic. The setup for this project is very easy. We're going to turn on dip switch 2, 3, 4, 5, 6, and 7, and we're going to leave dip switch 1 in the off position, and this means that we'll be using GPIOs 4 through 9 on the Atmega 328PU to control the LCD. We're going to force the LCD on by using this jumper. We will not be using software in this video to control the LCD backlight. So now that we've got our LCD hooked up, we're going to take our 3-pin wire connector and we're going to connect it to this header right here. This header right here is labeled KPD for keypad on the back, but we also use it for our PIR sensor. So what I'm going to do is, as you can see, there are 3 pins, 5V for 5 volts, AD for analog to digital, and GD for ground. So what I'm going to do is I'm going to connect the cable with the red wire facing left. So the red wire on the 5-volt line. The other side will connect to the keypad. The keypad has 3 pins on the back. One is VCC, which is 5 volts, one is GND for ground, and one is out. So what we're going to do is we're going to connect red to VCC, black to out, and white to GND. Now the explanation of this schematic might be a little bit difficult to follow. I have linked another tutorial video that I made a long time ago on resistor dividers, and you might want to have a look at that. So the basic understanding here is that we are dividing down 5 volts connected to the VCC line several times using the same value of resistor. We are using 11 different resistors of the same value, 2.2K, along the left-hand side, all the way down to ground. And each button is connected to a different spot between each of those resistors. So that means that we're going to get the same amount of voltage dropped along each of those dividers. So we're going to roughly see just under 500 millivolts dropped along each resistor. So we'll see a different voltage for each button. So when each of those buttons is pushed, it connects that specific area of the resistor divider to the output line. Now the output line, when no button is being pushed, is connected to a 100k ohm pull down resistor, which is connected to the signal line, which connects to the Arduino Playbot on analog pin 4. Now again, the reason for this is because when no button is being pressed, we don't want for analog pin 4 to be left floating. Floating means unconnected. If it's left unconnected, we're going to see all sorts of weird stuff on the line. It needs to be pulled down to ground through this pull down bleeder resistor. Now because we have that resistor there, when we push a button, it's going to this 100k ohm resistor is going to offset the voltage a little bit, and we're going to correct that in software, or rather we're going to compensate through software. So if you look at the upper left resistor, it's connected to VCC, which is connected directly to the VCC line on the upper right. So we've got 5 volts there. After one resistor, we'll see roughly 4.5 volts, and that's connected to the upper left button. When that's pushed, it connects that roughly 4.5 volts directly to the output line. if we press the lower button, the middle lowest button, we'll see between 400 and 500 millivolts there, because all of the voltages have been dropped along the first 10 resistors. And so when we press that button, it'll send roughly 400, 500 millivolts to the output line. So what's going to happen is the analog pin is going to read this, but the software in our upcoming videos waits for a voltage that's higher than, say, 20 millivolts or 40 millivolts. So it knows to stay dormant, the program knows to stay dormant up until it reads a certain value. When it reads a certain value, it knows that there's a button has been pushed, but buttons have mechanical bounce, so we add in a short delay before we read the actual value on that button, and that's called software debounce. There are hardware debounce circuits, but it's wasteful. We just need to add in a short 10 millisecond delay to get rid of that bounce, and then the analog pin will be able to properly read the settled voltage when you're pressing and holding that button. So let's actually have a look at the program. So because I want for you to see the LCD, I'm going to zoom in on the LCD. I'm going to tell you which buttons I'm pressing. Because I'm doing this because my camera doesn't seem to like the LCD too much. To the human eye, it looks great. To my camera, not so much. So what I'm going to do is I'm going to zoom in on the LCD, and I'm going to press each button, and I'm going to explain what you see. So when we're not pressing any button, we should see roughly a value of 0. And if you see it change to 1 or 2, that's just signal noise. And if we press and hold the button, we're likely going to see just a little bit of noise regardless. So I'm going to press the lower button, 10. So I get a digital value of 89. 89 out of a possible 1024. So now I'll start at the upper left, just like the schematic that we talked about. We should see between 900 and 1000. So 910, 912, 910. So again, it's just changing a little bit. It's updating just a little bit. And that's just because it's reading a little bit of line noise. But that line noise is easy to filter out just by making basically a software that says, is the button more than 850 but less than 950? If so, you're pressing button 1. Let me press button 5, which is roughly right in the middle. We should see roughly, give or take, 500. 526. And I'll press button 2, so we should see, I think just about 800, 800 and a bit. 803, 809, 809. So I'll let go. So this program just allows for you to experiment with how the analog pin 4, is reading the voltages when you press the button. So next, in our next project, project number 11, what we'll do is we'll create a decoding software that doesn't give us the digital value. It gives us a decoded value between button 0 or button 1 and button 10. Thanks for watching, everyone. Stay tuned for the next video. If you haven't already, check out the Kickstarter link below. And again, I'll post the link to another resistor divider video that gives you a much better explanation that I've provided in this video. Thanks again for watching, and have a great weekend, everybody. Oh, and happy St. Patrick's Day.